Welcome back, students, to eCoreAcademy. My name is Anita Raj, and I'm one of the teachers and founders here. Today, I have a new Algebra 2 lesson prepared for all of you, and as you can see, it's on quadratics. With this video, we start a new unit in Algebra 2 on quadratics. Many of you who have already been in Algebra 1 may be familiar with this word, quadratics. Well, the reason we're doing it again in Algebra 2, like I've told you before, is because we build off of basic fundamentals, concepts, principles, and so forth that we learned in Algebra 1. We build off of them in Algebra 2. So today we're going to be kicking off our Algebra 2 quadratic unit with quadratic functions and transformations. As you can see, this is part 1. It's going to be 3 parts. The reason I've done this is because I wanted to take the first lesson and chunk it into 3 bite-sized parts for all of you students who find it easier to digest shorter videos. So that's the purpose of putting it into 3 parts. It's going to be an introduction to quadratics through the lens of a higher level math student and Algebra 2 student. That's how we're going to be looking at quadratics in this video and the others to come in our Algebra 2 unit. Before I even dive into the content planned for today, please pause the video and like the video. I would really appreciate it. Also, subscribe to our channel to join our ever-expanding student community. Hit the post notification bell so you're notified of all of our latest posts, and also utilize our social media accounts in the description box below so you can share our channel using those socials to your family and friends who would really appreciate having a platform like eCoreAcademy to learn during quarantine. Lastly, don't be afraid to drop a comment down below about how you feel about our videos because we love interacting with all of our students. All right, let's get right into the content planned for today. So the first thing I want to go over are quadratics in real life. Usually we save real life applications for the ends of our lessons, but why don't we just start off with a bang? Why don't we start off by looking at quadratics in real life? And I'll show you what I mean. So look at this picture right here. First, let's identify what we can actually see in this picture. Well, we see this truck, and we also see these people getting launched into the air. So what is this? How many of you have heard about a human cannonball? Well, think of a regular cannonball machine, but instead of putting a cannon inside, you put a human inside and you launch them high into the air, and the human will glide through the air, and then a net will be awaiting them at the end to catch them. So that is what a human cannonball looks like. So how does this apply to quadratics? Well, let's take a look at the description I've written below this picture. In the picture, you can see a human cannonball launching people. Here you see the actual cannon, and then the human acts as the ball, and this is just the human as the human progresses through the arch that is formed when you're launched up into the air and then you descend back towards the ground by the pull of gravity. Look at this orange line. Think about what kind of shape it looks like. It looks almost like a bridge. It looks like an arch. Well, we often see these shapes in quadratics, and I'll tell you what I mean in the upcoming description. The path of the human cannonball is shown as the human is launched upwards and then comes back down to hit the target at the end. So this archway, this orange line represents the path the human is traveling. And the human is launched upwards. As you can see, this is upward like trajectory up here. And then the human comes back down and then hits the target, which is this net. So net is the target. And this is at the very end. So the human will finally hit the end. So what is this shape? What is this arch that looks like a bridge as the human ascends and then descends? Well, the shape looks like a parabola. And a parabola is the word that we use to describe the graph of a quadratic function. So if we have a quadratic equation, if we graph it on a coordinate plane, the curvature will look a lot like this. The shape that we get from the graph of a parabola from a graph of a quadratic will look a lot like this. We call this special shape a parabola. I have it down here. So we call this a parabola. All right, let's go to our next slide. So we're going to be looking at some terminology. So we're going to take a look at some words and concepts you should know which pertain to quadratics. We're going to be referring to these words and concepts a lot, so it is mandatory that you know what these words mean. Okay, so let's look at what is a quadratic. This slide is going to be answering that question for all of you. So quadratics are algebraic equations where the highest degree of the exponent is a square. So what does this mean? So if you think about a linear equation, let me write one down here for you. Y equals mx plus b. So that is your linear equation. Well, a quadratic looks a lot like that, but if you look here, the highest degree of the exponent is 1, x to the power of 1. A quadratic is different in that it would be looking more like y equals x squared. So the highest degree of the exponent would be a square, and that usually goes with your x. So that is what this means. Exponent is a square. So the highest degree of the exponent is a square. Next, we'll look at the word parabola. So a parabola is a curving graph that represents a quadratic equation. If you remember from this slide, we see a parabola shape. So that is what we would use to describe a quadratic. That's what a quadratic would look like. A parabola can look something like this on a graph. It could look something like this. It's just this arched looking graph, and this is what represents a parabola. Okay, so now let's look at forms of quadratic. So how will you see these quadratic equations given to you? I showed you y equals x squared on the last slide. Well, we have as it says here, a quadratic can be given in one of the two following forms. So we have two main forms that we write quadratic equations in. The first is standard form, which is right here. It's y equals ax squared plus bx plus c. So remember that key part, y equals x squared. You have to have a square exponent for this to be a quadratic. A, b, and c in this are constants, are your coefficients, and they're constants. So they'd be numbers like -1, 0.2. They're not variables, they're actual numbers. Okay, so the other form would be vertex form. This is y equals a times x minus h whole squared plus k. So the reason this is vertex form is because a quadratic equations graph, which is a parabola, has a vertex. We'll be talking about what a vertex is later on. But for you to know, a vertex is a point on a parabola, a very important point. So this form you would use this form when you have the vertex of the parabola given. And the vertex of a parabola would be written in this case as hk. Just how you have xy, you have hk using this vertex form, which is right here. H is right here, K is right here. You would plug those in, and then you would find out A. A just talks about if your parabola is reflected over the x-axis. Like, is the range less than 0 or greater than 0? Is it reflected over the x or over the y-axis? Is it compressed, or does it widen? Things like that. That's what A determines. Okay, now let's look at graph characteristics. So you have the axis of symmetry. It's the line that divides a parabola into two parts so that the parts are mirror images of each other, as in they are symmetrical. So let's look at what this means. So I'm just going to draw a mock coordinate plane right here. I'm sorry if it's kind of bad, but that's my mock coordinate plane. And then if I have a parabola like that, your axis of symmetry would be what divides this parabola perfectly into two halves. So it'd be a line that goes straight down the middle where the vertex is. The vertex is like your center point of your whole parabola. This axis of symmetry would go right down the middle and then divide it into your right half and then your left half. And these two halves would be perfectly identical to each other. So they would be mirror images. If you put them on top of each other, they would be perfectly identical to each other. So that's what the axis of symmetry is. Next, let's look at the vertex, this vertex we keep talking about. It's the point where the parabola intersects the axis of symmetry. It's also called the highest, maximum, or lowest minimum point of the parabola. So if you look back here to this drawing, the point where the parabola intersects the axis of symmetry. Well, if this was our axis of symmetry and this was our parabola, the vertex is right here. It's where these 2 points intersect, and the vertex lies on the axis of symmetry of your parabola. It's also called the highest, maximum, or lowest minimum point. So maximum or minimum point of the parabola. Here you see this vertex is at the very bottom. So this is what, as I drew before, this is what parabolas would look like. Either they would look like that or they would look like that. These both are considered parabolas. So in this case, your vertex is down here. It's the lowest that your parabola will go. So it will be your minimum point. Here, your vertex is up here. So it is the highest your parabola will go. So it would be your maximum. That's what they mean by saying maximum or minimum point of the parabola. Okay, so now we've gotten to the practice problem. So together, let's work out a problem so you can jog your memory of solving quadratics from Algebra 1. If we graph it and then look at some characteristics of that graph is what I mean by looking at this problem. Hopefully you'll remember some of those basics that you learned in Algebra 1 about quadratics. Okay, so here is the problem I'm going to give you. Sketch the parabolas of y equals 1/4 x squared and y equals negative 1/4 x squared on the same axis. How do the graphs compare to each other and the parent function? Identify the parabola, axis of symmetry, vertex, and give 2 pairs of corresponding points, 1 pair for each graph. So, I know this is a pretty long problem, but it actually is quite simple if you break it down into different parts. If you understand and organize the information and understand what it is the problem is asking you to solve for. So let's look at part 1 of the solution. So let me just have all these parts come up. This is part 1 of our solution. So what are we addressing here? We're going to be identifying the parabola in this case, which means by identify the parabola, what we mean is we're actually going to graph the parabola. So that is the first part. Even here, they asked us to sketch the parabolas of these 2 equations. So y equals 1/4 x squared and y equals negative 1/4 x squared. So that's what we're going to be doing right here. So I wrote the equations here, y equals 1/4 x squared and y equals negative 1/4 x squared. This equation is in this bluish color, this reddish color, this light reddish color, and this equation is in this bluish color. That's why I just made the box around them of the corresponding colors. So our first approach would be to graph these parabolas. Well, how would we do it? We're given the equation, right? So why don't we make an XY table as we usually do? So what we did was we made an XY table and then we picked X points. So we need to plug X into this equation, X points of our choosing, and we'll get the corresponding Y point, and then we'll get a coordinate that we can plot on this plane so that we can eventually connect the coordinates into a parabola. So the basic points you normally want to go for when you have a parabola are -2, -1, 0, 1, and 2. They're very much the easiest, and if you see 0 is our central number here, and then these values just go downward, and then these values just go upward. They correspond to each one another. So this would be like your perfect 5 for trying to find values of a parabola. So these are the ones I used. You can even see here for this x column, -2, -1, 0, 1, and 2. Be the easiest to compare and easiest to plug into these equations. Although these equations are relatively simple, we want to make it even more simpler for ourselves by using these values. So if I plug -2 into y equals 1/4 x squared, I get -2 squared, which is 4, times 1/4 is 1. Then I plug -1 in. -1 squared is 1. 1 times 1/4 is 1/4. Then I plug 0 in. 0 squared is 0. 0 times 1/4 is 0. Then I plug 1 in. 1 squared is 1. 1 times 1/4 is 1/4. Then I plug 2 in. 2 squared is 4. 4 times 1/4 is 1. So I have this whole table figured out. Let's move on to this one. So I have my -2. So I'm going to plug -2 into y equals -1/4 x squared. So -2 squared is 4. 4 times negative 1/4 is negative 1. Remember, there's a negative sign here. Then we have negative 1. Negative 1 squared would be 1, and 1 times negative 1/4 is negative 1/4. Then we have 0. 0 squared is 0. 0 times a negative 1/4 is just 0. Then we have 1. 1 squared is 1. 1 times negative 1/4 is negative 1/4. And lastly, we have 2. So 2 squared is 4. 4 times negative 1/4 is simply negative 1. So now that we have all these points, we simply just graph them on a coordinate plane, and then we connect the points of these individual graphs. So you would connect all these points for this equation, for this quadratic equation, then you would connect all of these points for this quadratic equation, and that's how you get these two graphs. So this graph right here corresponds to this equation, and then this graph down here corresponds to this equation. So as you can see, we sketched the parabolas. They correspond to one another because they're reflected. You see how this one is reflected. These are a reflection of each other over the axes. Okay, so now let's address the second part of the problem, which is pretty much the rest of this. How do the graphs compare to each other in the parent function? Remember the parent function, let me just write it up here. Y equals x squared. That's your parent quadratic function. How do they compare to the parent function? And then identify the axis of symmetry, vertex, and give 2 pairs of corresponding points, 1 pair for each graph. So we're going to be doing that on the next slide. So I just rewrote the problem up here so we can see it. Let's talk about the solution part 2. The first thing I did was I gave 2 pairs of corresponding points, 1 pair for each graph. So what do I mean by corresponding points? Well, if we go to the previous slide, what do we mean by corresponding points? So corresponding points would be points that are pretty much on the same or similar horizontally. So if you see negative 2, 1, negative 2, 1 is right here, and then you have 2, 1, which is right here. So these share the same y value, but they're different x values. They correspond to one another in that regard, and they're both part of the same graph. So that's what we mean by corresponding points. So all you have to do is pick a pair of corresponding points from each column here, and that's what I did. I just picked from the first graph negative 2, 1, and 2, 1, like I just showed you, and from the second graph negative 1, negative 1/4, and 1, 1/4. I'll show you back on the previous slide. Okay, so negative 1, 1/4 would be somewhere right here, and then you would have 1, negative 1/4 would be something like right over here. Okay, so now that we have our corresponding points down, what is the next thing we need to address? Well, we're going to be comparing these. So when we say compare means compare. Let me just write it up here. Sorry about my bad handwriting. I'm trying to use a mouse. Compare and contrast. So we're trying to find the similarities, but we're also trying to find the differences between these two graphs that I have on the previous slide. So how are we going to do that? Well, let's consider these factors. Identify the parabola. Okay, we did that. How about the axis of symmetry? And then we have the vertex. And then what about the domain and range? Look at all these other factors that we can compare and contrast. Look down here. The first thing I compared was the vertex. These graphs have the same vertex. So let's go back onto the last slide. And if you see, these have the same vertex. The vertex is 0, 0 right here. So they share a vertex. Also, they have the same axis of symmetry. So x equals 0, which is pretty much the y-axis. That's where the vertex was. That's what divided both of them in half. So let's just go back to the previous slide so I can show this to you. So just go straight down the middle. That's what divides these two parabolas in half, in mirror images. So next, let's look at the same domains. So the domains are the same, but the ranges are different. Okay, so let's look at the previous slide so that we can identify this. So for any parabola, your domain will be negative infinity to positive infinity. Why is that? Well, your parabola infinitely extends in both directions and it encompasses all possible x values. Same with this one down here. So they have the same domain, and this domain is shared by all parabolas. Even if it doesn't look like it on the graph, it just extends forever and forever in these directions. However, the domains are different. Domain is your y values. Well, here, our domain would be bracket 0 to positive infinity for this equation, because the least this equation is 0. It's equal to 0, but it's nothing less than 0. It just continues upward in a positive direction. This graph has the opposite predicament. This graph is negative infinity to 0. And remember, we put a bracket next to 0. And I'll show you on the next slide how we would write that in interval notation. Remember, in higher level maths, you would write these domains and ranges in interval notation. So this would pretty much just be negative infinity because it encompasses all the negative y values, but its maximum value, which would be the vertex, it doesn't go greater than 0. So it's no positive value. And we write that on the next slide in vertex. In the vertex, and we write the domain. So the domain would be negative infinity to positive infinity. And the range is the first one. The least value would be 0. So we put a bracket next to 0, and it goes to positive infinity. And then the other equation, the one that dipped downward, the blue one, it encompasses all negative y values, but the largest it'll be 0. So we just put a bracket to show that it was also equal to 0. And lastly, let's look at how these two quadratic equations compare to the parent function. So remember, the parent function is y equals x squared. This is your parent function. So how does it compare regarding shape? Well, if you see y equals 1/4 x, if you think of it, I didn't draw it, but it actually is a bit wider than the parent function y equals x squared. So this is pretty much y equals 1x squared. This is y equals 1/4 x. So it's a little bit wider. This would be like the parent function, and then this would be the functions that we graphed. They're both a little bit wider. This is called a vertical compression. So if the coefficient before the x, like in it, this should be x squared. Pardon me. It should be y equals 1/4 x squared and y equals negative 1/4 x squared. But if these values that you see right here, this 1/4, if it's less than 1, we call it a vertical compression. If it's greater than 1, well, then we call that a vertical stretch. Because if you think about it vertically, I want to say it looks fatter. It would look fatter than the parent function. The parent function would look like that. What we just graphed would look a little bit wider. So it's a vertical compression because it's compressed vertically. So it's like squeezed downward vertically. If this value was greater than 1, it would be even more skinny looking. So that would be a vertical stretch. It's being stretched even more vertically. So that's what we would call it. Instead of saying wider, what we would call it a vertical compression. And lastly, it's a reflection over the x-axis, especially this y equals 1/4 x squared. That's a reflection over the x-axis. The normal parabola would look like, the normal quadratic equation would look like this with positive 1/4, but this is a negative 1/4, so it's a reflection over the x-axis. So this would be like the normal parabola, your positive, and reflected over the the x-axis, it would be a reflection like that, which is what we also graphed with a negative 1/4 x squared. Okay, so that's all I have for you today. I hope you enjoyed that lesson. I hope it was a good review for many of you. We went through that pretty quickly, but you should know most of those terms. Hopefully I covered them. Hopefully my drawing was good enough for many of you. It'll get better as we go through these lessons. But again, hopefully that was helpful. We'll get into part 2 and part 3, looking at more terms, looking at more transformation side of quadratics, and then we'll be doing some practice problems together. I love doing practice problems with all of you. So that's all we have for today. Please like this video again and subscribe to join our student community. Also, hit the post notification bell and also share using our socials in the description box below. You can also drop a comment if you want to say anything to us regarding this video. Our website link is right here. It is eCoreAcademy.org. We'll actually have an official website going up soon. Right now, it'll redirect you back to our YouTube, but when our website goes up, it'll have a plethora of stuff not available on our YouTube, including notes, presentations, simulations, quizzes, and so forth. So definitely utilize that. It's at your fingertips. And lastly, for any personal or business inquiries that you would rather not put in the comments, use our Gmail, eCoreAcademy@gmail.com. We check it frequently. If you have anything you want to let us know, utilize that. All right, that's all I have for you today. Please look out for part 2 of quadratic functions and transformations, and I'll be getting back to you soon. Have a great day.